Hi everyone, welcome back to physics. Today is the first lesson for Unit 1, and at this point there is an assumption that you already have downloaded your lessons from the PDF file from Google Classroom, and it depends on where you're at in terms of understanding how to use Kami. I would strongly suggest and recommend you figure out how to take notes on Kami because most of your Chromebook you should be able to use the pencil and be able to take notes on your PDF file. So if you are not able to at this point, can you please make sure you go watch the other video of how to export a proper PDF note on Kami and how to download the Chrome extension so that you can get used to that. Another option is if you do have access to a printer, you're totally welcome to print out the notes and fill out the notes, or other than that, if you can't utilize Kami, you are not able to write on your Chromebook or for whatever reason, and you don't have a printer, it is totally okay to just use a pad of paper and take notes. Okay? At this point, we're not going to be handing out any paper. Either you're in the classroom or you're at home. We will not be handing out handouts. Like, I won't be printing anything for you for safety reasons, so please understand that. Okay? So, assuming that you have your note open, this is the beginning review of grade 11 physics. And notice at the top of the page, you have textbook reference 1.1 and 1.2. All those will be included in your Google Classroom post as well. So if anytime you need to refer to that, it is there. So I'm not actually go through the definition because these are definitions from last year and they go from page 8 to page 16. I do want you to go through them and learn it on your own. So at this point, if you would like to pause the video and actually just quickly start filling things out, things to watch out for are like what is scalar and what's vector. That's a big term. And then other things are just definition, displacement, speed, velocity, what's a secant, what's a tangent, how do you do the graphing. So these are all the terms that I would like you to know before you actually watch the video as I'm teaching it. Okay, now that you have reviewed some of the terms, I just wanted to go into a little bit of a details of some of these definitions and kind of stressing, how do we do the directions and picky things like that. Okay, just in case if you've forgotten. The first term is displacement. Displacement is a vector quantities. Hopefully you remember that whenever something is a vector, we use an arrow to represent, like kind of put on top of the symbol to represent that it does have a direction. The equation for displacement is delta D is dF minus di. So dF sometimes could be done as d2, which is also means final, minus d1. Okay, so those two are interchangeable. And keep in mind that displacement, we don't really care about what happened in between. All we care about is the starting point and the ending point. So if I demonstrate using like a number line here, so if this is 0, that's kind of like our reference point. And then they're going to tell you, oh, a dog has started 2 meters east. So where is east? You have to have an assumption of direction. So in this particular one, I'm just going to make an example that anything to the right, east, I'm going to put it on the right, and that is the positive value. So meaning if I say plus 5 meters, that is 5 from the 0. So I'm just going to write some numbers down. Okay. And then anything to the left actually means the west. West compared to the reference point that we made. Okay, so if I tell you something has started off right here, if this is the beginning, if this is the starting point, call this D1. If an object is at a starting point at 10, and then I'm telling you that this guy now I'm just going to do some scribbling, have traveled, say, all the way to negative 20, and then come back to, say, negative 5. Okay? We actually don't really care about anything that is in between. All we really care about is the starting point and the ending point. We only care about D1 and this point called the D2, which is the final position. Okay, so D1 is going to be 10. I'm going to just assume that this is in meters. I'm going to put positive because it's on the east side. And then the D2, in this case, is going to be at negative 5, meaning to the west. And if we plugged it into the equation, since delta D is is d2 minus d1. I will write that this is -5 minus 10, giving me -15 meters. But what does -15 meters means? It really means the change in the position from the starting point, which is at the 10. I have traveled this far. That thick purple line is the actual displacement, the change in position. Notice that it's pointing to the west direction. Okay, so when I actually write my final answer, I would write -15 meters, but don't forget my assumption is an east. That's why I have a negative east, meaning west. So this really is a 15 meters east, or in another hand, you could say that this is also 15 meters to the west, which is represented by this big arrow here. Okay, so just remember, things in between, we don't care. We only care about starting point to the ending point, and just pay attention to the directions. We will talk more about that. Okay, speed. Speed is a scalar. And for scalar quantities, we do not write the arrow. Okay, so sometimes I usually just magnify the speed. The equation is VAV equals to delta D over T, distance over time. Okay. Oops. Another way, I actually would just not even write the AV and just say delta D over T, so total distance. And then on the other hand, velocity, it's VAV over delta D with an arrow, which is displacement over time. So I don't even write the AV at all. I just write what's the displacement, starting point to ending point. So this is the two that I actually use closely. If I use the example that I gave just now in terms of distance and displacement, if you go back to my lovely drawing here, if I actually focus on what is distance and what displacement for the same action, for this guy who's traveling on this number line, the calculations for speed and displacement would be different. Okay, so if you want to take a look quickly, because if I take a look at this picture here, do you see how the total distance, I went from 10 all the way to 20. So 10 all the way to 20, I've traveled 30 meters. And then I go from 20 to 15, see this little chunk here? I would have traveled a total distance of 30 plus 15. So if I actually go back to here with the calculation, the speed will actually be the total distance travel over whatever the time. But if I were to calculate displacement, I mean the velocity, we calculate the displacement to be 15 meters west over whatever the time is. The time would be the same because it's the same actions. Do you notice that the two answers might be different, right? So in grade 11, we would have asked you a question, give a scenario when the speed and the displacement is not, speed and velocity is not the same. Hopefully by this point, you get that if there's any change in directions, then your distance and your displacement would be different, causing your speed and velocity to be different. The next concept we're going to cover is called acceleration. Definition for acceleration is change in velocity divided by the time, so the rate in change in velocity. So basically, how quickly are you speeding up or slowing down? The equation is acceleration is change in velocity over time, which equals to final velocity minus the initial velocity. So dropping the AV again. I don't need you to write the AV. So A is V2 minus V1 over delta T. I don't know if you remember, that is one of your high fives if you rearrange the equation for V2. Okay, but at this point, we're just going to highlight this. Okay, and the unit for acceleration, most of the time, probably 99% of the time, is meters per second square. Moving on to graphical analysis, there's 3 graphs that we have been talking about. And if you wanted to just quickly talk about what each of them stands for, a position time graph is basically talking about where you are at what time. And a lot of time, a position time graph can be easily understand from the number line. Oops. Keep putting the negatives. I'm just going to put. Okay, so say for example, if I tell you I have this guy who is standing right here, and he just stood there and he doesn't move. And if you take a look at the bottom graph, the first graph on the DT graph, I always like to put little numbers on my graph to help me interpret, because most of the time it's going to be on your multiple choice or something like that. I like to put little number to represent for me. Do you see this whole point? He's staying at the 4. So, meaning he's staying at there. So, meaning the guy is not moving. The description for this object is he's maintaining stationary. Okay. If it's a stationary, I don't need a direction. But if you're telling me if it's traveling at a constant velocity or speeding up like that, please do put a direction. So this one is stationary, so I'm not going to put a direction. Okay. And then now moving on to the velocity time graph. Okay. Velocity time graph, you're talking about at each of the time, how fast are you traveling? So you can almost think of it like I keep checking my speedometer on my car. So like at this time, I can see at 40 kilometers per hour. That is my speed at that time. And I keep making like a recording of how the speed is at each of the time, and then I do a graph. Okay, so if I go back to now this person who is stationary, if it's stationary, that means he's not moving anymore. So how fast are you moving when you're not moving at all? It's going to be all 0. So that's why the graph, it's a straight line at the bottom. Okay. And then the last graph, which is an acceleration time graph, it's are you speeding up or are you slowing down? What is the rate? Okay, so how quickly are you speeding up and how quickly are you slowing down? Okay, so back to this first example. If I have a person who's stationary and he's not moving, and you ask me on the third graph, how quickly are you speeding up or slowing down? Well, I'm not even moving. Of course, I'm not speeding up or slowing down. I have a graph that is a 0. Okay, moving on to this. I am letting you start out with here. Okay, so remember I said it would be helpful if you put some numbers in here to represent. VT graph, just now we talked about if it's a VT graph, meaning how quickly am I moving. So if I make it up, if I say this is 5 meters per second from 0 to 5 seconds. So if I tell you the whole trip, I am traveling at 5 meters per second. Do you see how the line is a horizontal line, meaning it's staying the same? So I do find it helpful if I first write out what it is first. So I'm going to say that this is going at a constant velocity. Okay, and whenever you're describing a motion, don't forget to include the directions. This one doesn't include, like on the axes, it doesn't say east or right or whatever. In this case, we just assume that this is forward because it's a positive value. We just assume it's forward. So I'm just asking you to make a little note to yourself. Whenever you're describing motion, don't forget to include direction. And if I wanted to now take a look at this graph to the right, which is the acceleration time graph. So let's think about it. If I am going at a constant velocity, I'm not speeding up, I'm not slowing down, I'm keeping that speed. And I'm asking you, are you speeding up or slowing down? I am not, because we already said we're not speeding up or slowing down. We're keeping that 5 meters per second. So therefore your acceleration is also going to be 0. But on the other hand, if we come back to the left and we're going to think about what is the position time graph. So where are you at a certain point? I started at 0, 0. So if I assume this guy with the number line started at 0, and I'm asking you if I am going at 5 meters per second, in 1 second, where am I going to be? I'm traveling 5 meters per second. So in 1 second, I should have traveled at 5. At 2 seconds, I would have traveled at 10. So if I make the little number grid here, I know that every second I increase at an equal increment, because every second I increase by 5, I end up with a diagonal straight line. So every time when it's a constant velocity, my position time graph should be a straight line. Okay, finally the second last one, they gave you the speed again. So velocity time graph. So let's make it up again. 0 to 5 seconds. I'm making this up. I was at a speed of 0. Do you see how I wasn't moving at first? And then my speed goes up higher and higher. So if I wasn't moving and I'm going faster and faster, I am experiencing a motion of acceleration. And because this is a positive value, I'm going to say forward. I'm accelerating forward. I do have a speeding up, meaning my acceleration time graph is going to be a speeding up. And if I'm speeding up, that means as I go further in the time, I go faster. I should be covering more and more distance as time goes on. My position time graph should be a curve. And then finally, my last one, 0 to 5 seconds again. At the beginning of the trip, I was going really fast. At the end of the trip, I was not moving at all. So I was going at 5 and then I stopped. What that means is I have to be decelerating. And the thing is, it is still a forward because the speed is still a positive. If you end up with a graph that have extended the negative and come down to the thing, you actually have started traveling backwards, but we haven't. Okay? And because this is a deceleration, I am experiencing a slowing down. I am decreasing and slowing down. My acceleration is a negative value. So it has to go underneath the 0 line. And then, now if I'm decelerating, I was going really fast at first. Eventually, I almost stopped and didn't move. So that means I would have covered more distance at the beginning and eventually level off and barely moved at all at the end. So now let's talk about using some of the equation and kind of just a standard format, just to get used to the format that we have worked on. I usually like to highlight my question. I read it through, I highlight the main point, and then I write out my given. So a hockey puck is passed from one player to another, 18 meters north, and then passed back 6.0 meters to the south. It takes a total of 3 seconds. Calculate the puck's distance traveled, displacement, average speed, and average velocity. Okay. You don't always have to draw a number line, but I don't know if that's going to be helpful for this one, but let's just see. Okay, a puck, this is your D1. Are we okay that this is your starting position? So don't forget the arrow. So I'm just going to say D1, initial position is 18 meters to the north. Okay, and then it's passed back to the final position, which is my D2, 6.0 meters to the south. And it takes a total, meaning your time, delta T, 3.0 seconds. Calculate the distance travel, which is delta D, the displacement, the speed goes with the distance, and the velocity goes with the displacement. So there's actually 4 things that I need. First part, distance. So I'm just going to draw a little number line here. Okay, so I was at 0. I started off at 18 meters north. I'm going to assume north to be positive in the number line. Okay, and then you can assume it the other way. Just make sure you swap it. Okay, pass back 6 meters south. So he ended up with 6 meters south, meaning a -6. Okay, one thing that you need to get used to, because we're not always going to be drawing a number line. One thing that I wanted you to keep in mind is whenever you're dealing with the given, you have to make sure all the directions are the same. Okay, so at the given, that's when you set your stage. There are things that I wanted you to keep in mind. Number one, you wanted to somehow make them all going to the same direction. And when you've done that, say in this question, I am going to change north or south is up to you. I'm just going to change the everything to north. Okay. By doing that, I've actually have to put a negative in front of the south and say north. Okay. So D2 is actually negative 6 meters to the north. Okay. Another thing that you have to keep in mind, we don't need to do it in here, is I want you to get used to putting things in SI units. Okay. This is especially true whenever we're dealing with like kinematic questions that involve accelerations and stuff like that. Some common units that you need to convert are from kilometers to meters. You multiply by 1000. Your metric conversion has to come back. Another very commonly used example is kilometers per hour. If you needed to convert it into meters per second, pause the video. What do? Do you remember? If I have to go from kilometers per hour to meters per second, what do? Hopefully, you're able to tell me that you have to divide it by 3.6. I'm not going to go through the long division and show you, but it is. You take your value and you divide it by 3.6. So those are the little pointers that we have done in grade 11. Hopefully, it's slowly coming back to you. All right, so keep going. All right, so total distance, to be honest with you, it doesn't matter direction. Total distance is, I take a look at this value. I went from 18 all the way to 6. So I have to 18 plus 6. Are we okay with that? That's your distance. Okay. There's actually not really going to be an equation for calculating the distance. I honestly would just write down that I know I went from 18 to 0, 0 to 6. So distance, no directions. So I got 24 meters. That is my distance. Okay. And then now they ask for the displacement. Displacement, we did have an equation just now. Okay, D2 minus D1. And D2 in this case is negative 6. Are you okay that we've actually changed, like we actually changed the value? They're all in north. Okay, so I'm going to show you proper format. So negative 6 minus D1. D1 is 18. Do you see that I got minus 6 minus 18? My displacement is negative 24. I write the unit down and be careful. If north is the direction that we have, then that means in my answer, it's also going to be north. So if you wanted to say, you can leave it as negative 24 meters north. That's not wrong. Or if you're actually understanding it, like if you take a look at it, I started at 18 and I traveled this way. Does it make sense that that means I've also traveled 24 meters to the south? So it's up to you. Both are okay. Okay, the next one is now speed and velocity. Speed is distance over time. Distance is 24 meters that we found. The time is 3, and it's going to be 8 meters per second. The unit for speed is meters per second. And then velocity is displacement over time. And displacement was 24 meters to the south. And time is 3. So 8 again, meters per second to the south. All right, so let's take a look at things that I do need you to pay attention to. Okay, one thing is sigdigs. Okay, I don't know if you recall sigdigs. This one has 2. I'm going to change the color of my pen. Okay, sigdigs for 18 is 2. I got 2 sigdigs in here. 6.0 is 2. 3.0 is also. So you always go back to your question to figure out your sigdigs, right? And we keep the minimum number of the sigdig. 2, 2, 2, the smallest number is 2. So I need 2 sigdigs. So don't forget, I actually need to put 8.0 for both of the answer. If it's 8, it only has one significant digit. And in order to make it one more, you have to put the 0.0. Okay, so that's one thing I needed you to pay attention to is sigdigs. Okay. The other things is, do you have your equation that are written when they're supposed to? We said for distance there is no equation. I wrote all my equation down. Did you put in like the work that you show your work? You always have to show your steps, right? And then the last one is when you express your answer. Did you put the proper sigdigs? We already talked about it. That's a communication mark. Did you put the right unit? and did you put the direction if it needed to be a direction? Okay, you go back to vector and scalar, right? If it's a scalar, we don't write the direction, but if it is a vector, you have to write a direction. So if you're missing any of that, you lose half a mark every single time, right? So just I know I'm not being very fast right now. I want it to be thorough to cover all the basics that we've talked about before. Okay, hopefully it's slowly coming back. It is a habit, but it'll come back to you. Question 2. A car passing a truck accelerating from 65 kilometers per hour east to 105 kilometers per hour east in 4 seconds. Calculate the average acceleration in kilometers per second and in meters per second. In kilometers per hour per second and then meters per second. So if you take a look at it, they're basically telling you to keep the speed in kilometers per hour and then just divide it by time. I hate questions like this. I honestly would never ask you to. I would need you to just get used to just doing it straight for meters per second. But I'll still follow it because that's what the example wanted us to do. So kilometers per hour, meaning that's your V1. V1 is 65 kilometers per hour east. When I see things like that, I would definitely right away take my calculator and convert it to meters per second. Okay, so remember how we set the conversion from kilometers per hour to meters per second is 65 divided by the 3.6. So you get whatever the value is. Some of you don't like rounding. Some of you can just leave this and just punch it in the calculator. So if I punch it in, it worked out to be, around approximately 18.06 meters per second. When you're doing your given and stuff, don't worry about sig digs. You basically would keep all the decimal places as much as you could until you get to your final point. That's when final answer is when you round. Okay, so V2 is 105 kilometers per hour to the east. So 105 divided by 3.6, I get 29.17 meters per second to the east. And they told me that the time it takes is 4. Acceleration, the equation for acceleration is V2 minus V1 over time. Oh yeah, by the way, I forgot to say, when I'm working along with the sample problem, I would like you to do it on your own too. The great thing about these videos are you can actually pause the video, get your answers, and then check it with me. Don't just wait and believe what I say. I want you to try it because sometimes you'll be surprised. Some of you take it for granted and then ended up, the order of operations or whatever, you're not getting the same answer as I am. So if that's the case, you would be able to realize, and then if you need to, you ask me questions, right? So V2 is 29 point, I forgot. I'm supposed to do the first part when it's not converted yet. So I'm going to do the first part first, leaving it in kilometers per hour per second. So I'm going to go V2, which is 105 kilometers per hour, minus 65 kilometers per hour, divided by the time, which is 4 seconds. So 40 divided by 4, so I get 10 kilometers per hour per second. I purposely left my units here just so that you can see what the unit came from. So 10, I need to worry about sig digs. 2 sig digs in this case. 10 only has 1. So if I want to be picky, this should be 1.0 times 10 to the 1 kilometers per hour per second. And this is to the east. Okay, so I worry about my sig digs. I have my unit. I have my directions. I have my equation and my sub-in and my answer. That's your 3 marks. Okay, I'm going to repeat the question. But this time I'm just going to be doing the other one using the one that is converted. So A, it's 29.17 minus 18.06 divided by 4. So you end up with 2.8. We got 2 significant digits, meters per second square to the east. All right, so assuming that this equation is repeating. Now we're getting to the exciting part of Unit 1 kinematics is your high fives. Okay, so these are your high fives, and can I challenge you to write your high five out right here at the bottom? So pause the video, write the 5 equation out. Okay, go. All right, now please check your answers. I'm sure you guys all did not cheat and did not look at the next page to copy out the equation, but I hope you also realize that you are required to know them and be able to use them. So these are the 5 equations. We've always used 1 and 2 at Wilson. The textbook likes to use F and I. It's up to you what you want to use as long as your equation is correct, right? Like what I mean by that is like different version writes the same. I don't know if you recognize, say for example, if I ask you to take a look at 2, equation 2 could be written differently, right? Instead of writing together divided by 2, they could also write it as an equation and multiply it by half and not do it at the bottom, right? So as long as your equation is correct, as in it will give you the same value and mathematically it's the same, it really doesn't matter. So I'm just going to erase this guy. Okay, this is how I like to use it. This is how I've always been using it. And if you take a look at the next page, it does have the 2 and I mean the F and the I, which is fine. And so summary, each of these equations, if you have been analyzing it before from unit 1 from grade 11, each of these high five always have 4 variables. Okay, if you take a look at every single one of them, equation 1, 2, 3, 4, 5 always have 4 variables. And if it's a simple kinematics equation, we always assume that we will need 3 givens and then 1 unknown. The reason for that is like any mathematical equation, right? Like say if I give you an example, 4x equals to 5, this is the only way you can solve for x, right? But if I give you like 28x plus y, you cannot solve for x and y because you don't have enough value. You only when it has one equation with one unknown that you're able to solve for this. But obviously there are exceptions, but at this point we're just going to starting simple. So it's important for you to recognize when you read from a problems, you need to pick out what are the givens and what is the unknown that they're looking for and find the appropriate equation. Because the other thing that you can analyze is take a look at equation 1. I have VF. If I check off VF, NBI, NA, and T, notice that whenever, like when I say the 3 givens and 1 unknown, as long as I have these 4 variables, I would be using equation 1. Okay, so that means I don't have a D1 for the first equation. Repeat the process. A, VF, V1T, this one doesn't have an acceleration. I have D, VI, A, and T, no VF. I have D, VF, A, and T, no VI. VF, VI, A, and D, no delta T. So notice that we give you an array of different equations to allow you to pick the correct one that you could use. But if you go back, we're not going to go through where they came from, but if you want to know where they came from this one graph, this graph right there, a VT graph, by either finding the slope of the line or the area under the line and do some manipulations of rearranging equation, the 5 equation came about. All right, so little tricky thing that I needed you to keep in mind, you need to find out hidden variables in your question. Okay, so if anytime, like this is just some example, I can't possibly name them all. If I tell you something start from rest, you can assume that V1 is 0. Okay, if I say, oh, I hit a tree, you can assume that, oh, it would have stopped and V2 is 0. I forgot the unit. Other thing which we will talk about is if something is free falling. If I throw a ball or tossed it or whatever, whenever I throw something, you are given that the acceleration due to gravity is 9.8 meters per second squared down. And along the line, if you're throwing something, if they ever say anything like, oh, I drop a ball, there is an assumption that V1 is 0. Okay, so it's not moving. These are a couple of examples. Or other thing would be like if I'm throwing something and I'm asking you, oh, what is the maximum height? Okay, it tells you that the V2 is 0. The maximum height is, it will, you know how like when you toss something up with a speed, it's slowed down by gravity to the point that it will stop and then start coming down again, right? So at the maximum height, if I'm considering this one leg, like from down to the maximum point, it has to stop before it starts to accelerate downwards again. Okay, so so this is the free fall. So if you can just highlight that, you already had that written down. Is whenever the force acting on it is force of gravity. Acceleration is downwards with 9.8 meters per second square. This is an assumption that you're very close to Earth's surface, right? If you're not, there are other assumptions. Like even I don't know. Some of you might not even have those lessons, but when we talked about gravitation, like the gravity at the equator is not going to be the gravity at the pole, just because the Earth is actually not completely spherical. But we'll cover that when we get to that. Okay, so let's do an example. Okay, so now we're moving on to acceleration due to gravity. We're talking about a falling stone takes 0.3. Please change this question. 0.30 seconds. Just add an extra 6 to travel past a window of 2.2 meters high. From what height above the top of the window was the stone drop? Oh, these are the harder types of questions. Okay, they're not a straightforward high five question. This one actually requires some thinking and drawing. So if you would like to, actually I would love it if you can stop the video, try out the question, and think about how to do that. Okay? So this is the window. They tell you that the window is 2.2 meters high. And they tell you that this piece of stone was actually dropped somewhere up here. It was dropped at the top. The actual answer that they want is they want to know what is this delta D for the top of the stone. But what you do know is that the time it takes to go past the window this time is 0.30 seconds. So it takes that long. So I need you to figure out what is the delta D at the top. So let's change some color here. All right. When this is being dropped, I'm just going to use the red to represent the top. When something is being dropped, V1 is 0. Because something is being dropped, it is experiencing acceleration due to gravity, which is 9.8 meters per second squared. What I do want to find is delta D. I still need one more given for the top part. Do you see that? Like, I remember how we said we need 3 given and 1 unknown. So from the top, I don't have enough value. So let's see in the middle part, okay? So the middle part where the stone is passing through the window, let's see what we know. Okay, so the middle part, I know the time is 0.3 seconds. I know that the displacement is 2.2 meters. And I don't know if you picked this one out. The stone is still experiencing acceleration due to gravity going downward. Oh, these are downward actually. This is going down. Right? I have 3 given. I need to look for something else that can kind of connect. You need to find the connection between the top and the bottom. What is the connection between that? Sometimes it is helpful for you to see what can I find, right? And so if you take a look at there are 5 variables in total. There's time, displacement, and A. That's what's in the question. I'm looking at the red part. Okay, so what can I find? You actually are left with 2 choices. You can find V1 or V2. Those are the only 2 that I could find. V1 is the speed up here at the top. V2 is the speed up down here at the bottom. If I want to find the connection between the 2 points, do I want to find the connection at the bottom or at the top? Actually, it's up to you. But I would probably find this one. Because if I found what V1 is, do you see the connection that the initial speed at the top of the window really is the final speed at the bottom of the green part. My V2 at the bottom has to be the same as the V1 that is at the bottom. Okay, so with that said, now I can figure out my 3 given and 1 unknown, find the equation. I have T, D, A, and V1. Hopefully, you will work hard to memorize your high fives and then figure out which equation. Some of you probably still remember it from grade 11. Okay, all right, so let's see. D, A, V1, and V2. So we're actually using equation 3. So the equation that I'm going to use is delta D equals V1 delta T plus 1/2 A delta T squared. So 2.2 equals V1 delta T plus 1/2 A delta T squared. Please use your calculator. Figure out what the answer is. So V1 worked out to be 5.863333. I'm not going to round right now because that's not my final answer. Okay, so finding that means I now have V2 for the green part. So I'm just going to fill that in. Sorry that this is getting a little squishy here. I'm just going to rewrite this V2 over here. So I've now found V2 for the top part is also 5.863. The final speed for the top half is that. So now I have V1, A, D, and V2. So I need to find the equation that only has these 4, but nothing else. So the equation that I'm going to use is equation number 5. Are you able to pick it out? So 5.863 squared equals V1 plus 2A delta D. So I'm going to fill in my numbers. So I'm going to, instead of punching in 5.863, I have that number in my calculator already. So I'm actually going to use the value that is in my calculator without rounding. I'm going to square it. Okay, and then I'm going to move the 2 over by dividing. So I'm going to divide it by 2 and then move the 9.8 over by dividing again because these are multiplying. So to move it over is opposite to that. And I got my value for delta D is equals to 1.754 something. And look at my SIGDIGs. I did change my value to with 2 SIGDIGs. So 2, and then the rest of them, 9.8 is also 2. So I'm going to keep 2 significant digits. So 1.8 meters down. Okay, last example of today's lesson. A truck with one headlight is traveling at a constant speed of 18 meters per second. When it's passed by a stop, okay, I'm just going to change the color, a stop police car. The cruiser set off in a pursuit at a constant acceleration of 2.2 meters. Do you see how there's 2 objects? So for sure there's going to be 2 data lists. They're asking you how far does the cruiser, sorry, wrong pen, how far does the cruiser travel before catching the truck, and how long does the pursuit last? All right, very good question. I believe you've learned this in grade 11, and it's not the straightforward question. Pause the video, try to figure it out, okay? And then start the video and watch again. So I'm going to use blue for the truck. So the truck is traveling at a constant velocity. I always still like to write it out because I know for something that's traveling at a constant velocity, I'm not using the high five. Okay, I'm actually just going to write it at the bottom just so I know this is the equation that I'll be using. When I'm traveling at a constant velocity, I will not be using the high five, only velocity displacement over time. It tells me that it is traveling at a constant speed is of 18 meters per second. Okay, and that's pretty much all I have. So let's take a look at the truck. I mean the police car. The police car would stop at first, so the initial velocity is 0. And then it tells me that it is accelerating at 2.2 meters per second squared. And it's asking me, when are they going to be caught up? Okay, so these types of question, I like to call it the chase question. Some people call it the catch-up question. And there is an assumption, what has to be the same in order for you to be caught up? What are the variables that has to be the same? Okay, so let's think about it, right? So I got a truck. This is my truck. I got a truck that is traveling at a constant speed of 18 meters per second the whole time. He just traveled like that. And then I got a police car. That's a light. I got the police car that wasn't moving at first. And then it's going to start accelerating. And I need to know, when are they caught up? Okay? What variable has to be the same? Usually, this is when I say, hey, raise your hand, answer the question. A lot of people tell me that when they're caught up, their final speed has to be the same. Is that true? Think about it. The truck has been traveling at 18 and is maintaining at a speed of 18. So if you say their V2 has to be the same, so you're saying that this police car wasn't moving, eventually speed up to 18 meters per second, and that's when I'm going to be caught up with this truck that has been traveling at 18 meters per second the whole time. Do you see what I'm getting at? The police car probably should be traveling a lot more than 18 in order to catch up with the missing speed that I didn't have before. Okay, so that means this assumption is wrong. Okay, your V2 is the same is not correct. Okay, so that's wrong. So let's just take the step. In order for you to be caught up, you actually need to be in the same place at the same time. That's when I'm actually caught up with someone. We both run the same amount of time and we ended up at the same final displacement. Okay, so every time with the caught up question, you need to keep in mind that both delta D and delta T must be the same between the two. Okay, so that is kind of the parameter that we will need. Okay, so how do we set it into the question? So that means I have delta T and delta D, even though I don't know what they are. They're an unknown, but don't forget, I also need the delta D and the delta T for the truck. I don't know what they are, but what I do know is that even though D and T are the unknown, I have two equations and two unknown. And in math, if you think back to that, you are able to solve for it. Okay, so let's start filling things in. So it's basically your x and y. Your d and t is like your x and y, and you got two equations, and then you'll be doing substitutions and figure out one by one what each of them are. Okay, so I'm going to fill in the numbers that I know. I know that v, so I'm going to start with the blue equation. V is 18 equals to d over t. That's my first equation. Okay, second equation, I have to figure it out. I didn't write it out yet. V1, A, T, and D. Because the car is accelerating, I could use one of the high five. So which high five am I using? So let's see. I'm going to be using the delta D is V1 delta T plus 1/2 A delta T squared. Because those are the four variables that I have. V2 is the one that I don't have, so I make sure I don't use the one with the V2. So D equals V1 is 0. Whenever something is 0, when I multiplied it, the whole term is gone, right? So this whole term is gone. 0 times, no matter what t is, it's going to be 0. So I'm just going to check that. 1/2 a t squared. Clean it up. D is 1.1 t squared. This is my equation 2. And when I have two equations and two unknown, I can now sub one into another. So I'm going to take equation 2 and I'm going to sub it into 1 because I already have D on its own for equation 2. I'll just sub it in. Okay, so 18 equals D over T. So 18 equals to D. Instead of writing D, I'm going to take my red equation and I'm going to put in the, instead of the D, I'm going to put in the 1.1 T squared divided by the original t squared and t squared divided by t. Do you see how this cancel with each other? So to rearrange the equation, I now have 18 equals to 1.1 t. So 18 divided by 1.1 t. I end up with t is 16.36 seconds. Sigdics are 2 sigdics, and because the question that I did solve for part B first, it did ask for how long, I do need to express it with the correct sigdics. So T, final answer, is 16 seconds. And then part A, I need to find out how far, meaning what T is. So you can plug it back into equation 1 or 2 of your choice and figure it out. So I'm just going to, since T is on the calculator, I'm just going to use equation 2 to solve for part A. I know D is 1.1 T squared. I won't use 16. I know I wrote 16 here. I'll actually use the value that is in my calculator, which is the 16.3636, right? I'll just actually take that value, square it, times the 1.1. You don't want to round until you absolutely have to at the end. So I got something like that without any rounding. This is no rounding at all. Okay, so this is the value that is in my final answer in the calculator. And then I need to round it to 2 significant digits. So sigdics has 2, so I need 2, meaning I'm going to round off everything to the back. And because that's less than 5, I'm going to be calling this 0. So the answer is 290 meters forward.